All right, let's check out some perpendicular bisectors. So perpendicular, meaning 90 degrees. Bisector, meaning cutting the segment into half in this particular case. So I'm just going to draw a segment, and the perpendicular bisector is going to be perpendicular and go through the midpoint. So that red line is the perpendicular bisector. And what that says is that if that's the midpoint, that means that is congruent to that, meaning equal in length, and that's 90 degrees or that's 90 degrees. Once one's 90, they're both 90. Okay, so let's talk about what happens here. It turns out that you can look at any point on the perpendicular bisector. That guy right there. Okay, some random point on the perpendicular bisector. And that we want to be able to do is we want to compare that dotted distance and that dotted distance. Okay, and what do you know? Well, the reflexive property, looking at the two triangles, says that for that left triangle and the right triangle, they both share that red side. Those sides are congruent because of the definition of a perpendicular bisector, and that angle is 90 degrees, so that angle is 90 degrees. And so for the two triangles, what do we now know? They are congruent. Why? Well, because we learned about triangle proofs. We know that side, angle, side, meaning double, 90, single, double, 90, single. So side, angle, side proves that the two triangles are congruent. But if the triangles are congruent, then we know that the corresponding parts of congruent triangles are congruent. So what do we now know? Well, now we know that every single corresponding piece is congruent, meaning that guy is congruent to that guy, which means what? What conclusion can we draw? We now can say that any point on the perpendicular bisector is equidistant from the two original endpoints. Meaning we can take any line we want, we can construct a perpendicular bisector, and we can take any point on it we want. A point here, a point here, a point here. Take any point on that perpendicular bisector, and we now know that for sure those lengths are congruent. So any point on the perpendicular bisector is equidistant to the endpoints of the segment. Cool, and that's now a theorem we know. It's called the perpendicular bisector theorem, but we proved it, right? I justified it, I didn't make this theorem up. It's pretty easy to justify too. We just use side, angle, side to prove the two triangles are congruent. And then we know that if the triangles are congruent, we know corresponding parts of congruent triangles are congruent, which proves that these two are the same length, meaning congruent, no matter where I would have put that dot. Wherever I put that dot, the two triangles are still going to have side, angle, side. Okay, put the dot here, put the dot here, meaning that distance and that distance have to be the same for the same reason as above. Okay, now let's look at a cool application of perpendicular bisectors. And what we're going to do is we're going to use it to find the circumcenter. Circumcenter. It's one of the versions of the center of a triangle. It might be my favorite, but I think they're all pretty cool. All right, this is a triangle. Let's pretend that I can find the perpendicular bisector for each one of these sides. Again, I'm going to eyeball it. It's going to be okay. So I'm going to come over here to the midpoint, and I'm going to draw what I believe to be the perpendicular bisector. Okay, and I'm going to come over to this guy, and I'm going to draw what I believe to be the perpendicular bisector. And then I'm going to come down to this guy, and I'm going to draw the perpendicular bisector. Something like that. Again, the 3 red lines are perpendicular bisectors, meaning I found the midpoint right here, and I drew a perpendicular line. Midpoint, midpoint, draw the perpendicular bisector. Here's the cool part. Number 1, the perpendicular bisectors all intersect right here, which is going to be the circumcenter, but that's not the cool part. Here's the cool part. What do we know about any point on a perpendicular bisector? It's equidistant to the endpoints of the segment. And I'm going to draw these in a dotted blue. So see how this point right here is on this perpendicular bisector for this segment? Doesn't that mean that this point must be equidistant from those 2 endpoints? It has to be. It's on the red, which is the perpendicular bisector. So these are congruent. But check it out. This dot is also on this red line. This red line is the perpendicular bisector for that segment. Well, that means that this point is equidistant from these 2 line segments. But if this is already a slash, then that's a slash. And check it out. What just happened? I just showed you that the circumcenter is actually the point in the circle, or excuse me, in the triangle, that's equidistant from the 3 original vertices. Circumcenter. Huge property. Equidistant to all 3 vertices. Okay, in my particular class, we talked about this being the Walmart theory or the Cedar Point theory, right? You got a huge population of people right here. You got a huge population of people right here. Maybe they're cities or maybe they're big neighborhoods, and you want to put a Walmart somewhere. Where are you going to put it? I don't know. You could make a case that you want to put the Walmart so that it's perfectly the same distance from that city, and that city. So where is it? It's in the circumcenter. How do you find the circumcenter? This guy. Take the 3 perpendicular bisectors, the intersection. Since you're on a perpendicular bisector, you have to be equidistant from the endpoint, and that is enough to show me that that and that and that are the same distances. And so our circumcenter is equidistant from the 3 vertices. And another kind of cool thing is that it is also the center of the circle that inscribes the triangle. We don't really use the circle that much. It's just kind of another cool property, but certainly way cool that we can actually apply perpendicular bisectors to find something, the circumcenter. And again, in my class, we called the circumcenter kind of the Walmart idea. Where are you going to put a Walmart if you want to have it equidistant from 3 separate big neighborhoods or maybe 3 small cities? You don't want to put a Walmart in one city. These 2 people are going to be upset. You might as well put it right there so it's the same distance from all of them. Okay? So that's perpendicular bisectors and then an application in terms of the circumcenter. Cool?